All right. So we've solved a few systems of equations now, and you can probably tell that, well, it's a bit exhausting, right? It's a decent amount of work to keep rewriting it all, right? The actual math itself isn't too bad, but rewriting all these equations all the time is a bit, time consuming. So is there a better way to do it? Well, thinking about the systems of equations that we've been solving, the variable names themselves aren't really that important, but the coefficients in the system of equations are, right? The things, in front of the variables, the numbers on the right side of the equal signs, these are the important pieces of information. So what we're going to do is keep track of those, but we're going to toss out all the other stuff. But we don't want to just write a bunch of numbers kind of willy-nilly around. We want to keep track of them in a nice way. And this is where something called a matrix come in, or plural, matrices come in. Right? So what is a matrix? Right? So a matrix, well, really it's just is a box of numbers. That's really what it is. What does it look like? Well, it looks like this. All right. Usually we use square brackets. Sometimes we use parentheses. It depends on kind of the book and the situation. One thing we never use are curly brackets. Right? And the way this fills in is A11, A12, A13, ... A1n. This should remind you of our general definition of a system of equations, right? And here, so this is row 1. Row 2 is going to be A1 or A21. Let me fix that 2 a little bit. A21, A22, A23, ... A2n. Right, and we read these subscripts just like we were in the system of equations earlier. Right, row 3, A31, A32, A33, and so on to A3n. Right, and then we can keep doing this until we fill up the matrix as big as it needs to go. So AM1, AM2, AM3, and AMN. Right? So here, this is column 1. Right? This is column 2. Column 3. This last one here is column N. All right. Over here, we get row 1, row 2, row 3, all the way to row M. Okay. So all of these numbers here, or all of these variable are constants in here. These are all just numbers, right? All of these A's just stand for numbers. All right. This is what we call an M by N matrix. All right. So this is an M by N matrix. All right. We're just kind of saying, like we could say a 4-foot by 10-foot table. If you think of that kind of stuff. Like for an actual physical table. This here, we just read it number of rows by number of columns. Okay? Each of these numbers inside the matrix is called an entry of the matrix. So Aij, this here is the ijth entry. Okay? When we read this, right? So if it were something like the 2-3 entry, okay, the first number tells us what row it belongs to. The second number tells us what column. So row 2, column 3 would be the A23 entry. Okay? So normally we denote a matrix by a capital letter. So this matrix here, we might call it capital A to stand for this whole thing. All right? Just a little bit of notation for the future here. When we refer to rows, we'll often say R1, R2, R3, all the way to RM for the rows, and C1, C2, C3. These are capital R's and C's. To CN for columns. All right? That'll help us out a bit later here. Okay? So in a matrix, right? If M equals N, so the matrix is so-called N by N, we call it a square matrix. So I'll call that matrix up there capital A. We say the matrix A is a square matrix. Right? And again, square matrix here is just meaning that it has the same number of rows and columns. It'll turn out for us that square matrices are quite important. Okay? All right, so that's another definition. Another one here is the entries A11, A22, A33, and so on. These make up the main diagonal. Right, of a matrix. All right, so that main diagonal back up here would be, well, it might not go all the way down to the corner. If M and N are equal, it'll go from the top left corner all the way down to the bottom right. If M and N are different, well, it's going to keep going until it hits the right edge or the bottom. It doesn't matter which one, just whatever one it hits first, it'll stop there. Right? Sometimes we don't even speak of a non-square matrix as having a main diagonal, but it's this is a pretty important diagonal here. So the A11, A22, A33, A44, just as many of those with the same subscript as you can get. All right. So why do we bring in matrices? Why does this matter? All right. Well, let's look at this here. So earlier we did the system of equations x1 minus 4x2 plus 3x3 equals 5 minus x1 plus 3x2 minus x3 equals negative 3, and 2x1 minus 4x3 equals 6. All right, so we had this system here. We have a way that we can rewrite this system here and turn it into a matrix. All right, what we're going to do is just keep all the important information. So x1 is the first column here, so I'm going to take the coefficients from these. So 1, minus 1, and 2. All right, take the coefficients from x2 in the next column. Negative 4, 3. There's no x2 here, so we just put a 0 there. The third column is 3, negative 1, negative 4. The fourth column here is 5, minus 3, and 6. All right, so we've taken the system and turned it into a matrix. Now, one thing the textbook doesn't do, but I find particularly helpful, is I want to separate out the numbers that come from variables and the numbers that come from the right side of the equation. Now, this is purely cosmetic. It doesn't affect anything we're going to do in any way. So it's up to you whether you want to write it. I think it's a good idea just to sort of keep track of what's going on. I like to draw a line right here to separate out the coefficients and the constants. All right, just so, even if it's just for personal comfort, it's a good way to keep track of this. All right? Now, given this here, this lets us create two things called the coefficient matrix and the constant matrix. Right? So the coefficient matrix is just this part right here with all the coefficients from our system of equations. Right. So I cheated a little bit. But the coefficient matrix is just the part that come from the variables. Right? This will be more important a bit later on. Right? And then we have here this part of the equation, or of the matrix, which we call the constant matrix. And again, this is something that'll be a bit more important as time goes on. But we can make these other smaller matrices as well. Right? Just as a little comment here, this is what we would call a 3x3 matrix. This here would be an example of a 3x1 matrix. Right? So maybe I'll write size. Right? We refer to the size of a matrix as the number of rows by the number of columns. Right? So actually we can even come back up here. This here is the size. Okay, so hopefully it makes sense how we're taking a system of equations and turning it into this matrix here. All right? So in the next video, I want to show you why we do this. We're going to resolve this exact same system of equations here, but we're going to do it with matrices.